session. Just 1 minute. Okay, let's start today's session. So, welcome everyone to week 5 of our NPTEL-PMRF problem solving sessions for the course Electronic Theory of Solids. First, a brief introduction of mine. I am Akshay. I am a PG student PMRF in the Solid State and Structure Chemistry Unit as a CEO of the Indian Institute of Science, ISC, Bangalore, India. I did my BTech MTech dual degree in the Department of Material Science and Engineering from IIT Kanpur. Just a minute. Right. Yeah. Okay, so I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL-PMRF TA for this course. Alright, so let's just start today's session. So I want to notice that also this week I have started this thing. So in the starting of the session, so today we are having session. So in the morning I had uploaded all these problems that we are going to solve in today's session in the Google Drive, the Google Drive link that you have where you, for your week content. So you can go to that Google Sheet and Google Sheet where the links for the lecture videos are, and then go to the Google Drive folder. And in that Google Drive folder, every morning when we will have this session, you can find the problems there, but the problems that we are going to solve in that session, and you can give them a shot. Okay, you can try them on your own, and later we will solve this problem in the sessions. All right. So let me just. That was just a brief announcement, because some people asked last time that they want these problems to be uploaded earlier in the session so that they can give it a shot. So from now for today's session as well, I had uploaded the problems, and from next time as well, the problems will be uploaded on that Google Drive link, and you can check out from there. Right. So let me just go full screen. Alright. So let's just start with today's session. Okay, let's just start with today's session. So the first problem we have is we have to determine the relation for effective mass and mobility for the following valence bands. So here we are given 3 bands basically. Okay, so let me just make it like this. So 3 bands are given to us, band 1, band 2, band 3, and we can see that they have a different curvature. So for this problem, we should remember that like we know that this effective mass m star. So we know that m star, which is our effective mass, it is inversely proportional to the curvature of the curve. So del square E by del square K square will be the curvature of the curve. Alright. So whatever of our dispersion curve, so whatever the curvature is, that is given by the double derivative of our energy dispersion. So that so our effective mass is going to be inversely proportional to this, and our mobility is inversely proportional to this effective mass. So these 2 things we need to remember for this problem, for this kind of problem. All right. Right. So you need to remember these 2 things. That the effective mass is inversely proportional to the curvature of the curve, and the mobility is inversely proportional to the effective mass. All right. Okay. So for this problem, now here we can see that here we can see that the curve number 3, which is in the green color, it has the highest curvature, and then we have the curvature, and then we have the one which has the lower curvature, and then the two one which is almost, we can look like it looks like flat, so it will have the lowest curvature. Alright, so that means del square epsilon, from this diagram we can see that del square epsilon by del k square of the third one is greater, it is larger than the del square E by del k square of the first curve, which is in pink, which is larger than the del square E by del k square of the second curve, which is our blue one. Alright, so this is the relation between the curvature. So as we know, our m star is inversely proportional to this. So m star of this third one, it means this effective mass of the third curve, this third band, green color band, will be less than that of the first band, which is the this pink color, and which will be less than that of the blue band. Alright, and since mobility is just inversely proportional to this effective mass, so we just reverse it again. So nu 3 star will be greater than nu 1 star, will be greater than no star is nothing, and will be greater than nu 2. Nu 3 will be greater than nu 1, will be greater than mu 2. Alright, so this was the problem. Okay, any doubt in this one? Right. So let's go to problem number 2. So in problem number 2, we have been asked like what is the velocity of an electron at the boundary of the first Brownian zone of a crystal. Alright, so we need to find the velocity of an electron at the boundary of the first Brownian zone. Now we know that velocity is given by if we have the energy dispersion of the electron, we have 1 by h cos gradient about k vector, energy dispersion E of k vector for an electron with energy dispersion epsilon of k vector. Alright, so this is how we give the velocity. Now since at the boundary of the Brownian zone, so we are asked the velocity of the electron at the boundary of the Brownian zone. So since at the boundary of the Brownian zone, this gradient of epsilon of k vector, that is 0. So we have the velocity equals to 0. Right, since the this gradient of epsilon of k vector, that is going to be 0 at the boundaries. Okay, so at the boundary we know that the band generally go like this. Alright, like in the 2D case, as you have seen, in the 1D case, if you remember, the bands are generally like this. So they are, so basically the this slope is generally 0. So del E by del K is equals to 0 at the boundaries. So because of this, the velocity of the electron, that is also going to be 0 at the boundary of the first Brownian zones. Alright, so this was our problem number 2. Now problem number 3. So in problem number 3, it is given that determine the relation between the temperatures T1, T2 and T3 in the below diagram. Here T0 is equal to 0. So we know that T0 is given here as 0 Kelvin. Alright, and T0 we can see that it is just a steep. So okay, it is 1 for less than T0, and for T0, for T greater than T0, it is 0. So as we know, since and it goes like, we know the Fermi-Dirac distribution, 1 upon 1 plus exponential of E minus EF by kBT. So this is the Fermi-Dirac distribution, or basically this is the this is this Fermi-Dirac distribution. So here we can see that, or what we can see that I can write this. So basically for different temperatures we are given the Fermi-Dirac distribution, how it looks like. Alright, and also like this will be like T1, this will be T2, and this will be T3. So it is not mentioned here, but it will be like this. Okay, so T1 curve is going like this, T2 temperature curve is going like this, and T3 temperature curve is going like this, and we need to find the relation between these temperatures T1, T2 and T3 based on this diagram. Alright, so here let me just write, so I can write this thing as 1 plus e to the power del E by kBT, right, where this del E is basically E minus EF. Okay, so del E is basically E minus EF, so we can write this as 1 upon 1 plus e to the power del E by kBT. So this is our Fermi distribution. Now for T not equals to 0, not equals to 0 Kelvin, okay, because for T equals to 0 we already know what it is, and now T we have some non-zero temperatures, we have this Fermi-Dirac distribution. So what you can write it as, for energies less than EF, we know that this del of E is going to be less than 0. Alright, so as T increases, this del E by kBT, this will also increase. So the magnitude wise, so basically you can see that since del E here, note that del of E for E less than EF, del of E is less than 0. Alright, so if I increase the temperature, so then del E by kBT, this will also increase. Basically the magnitude will decrease, but since it is a negative, so the value will increase, and therefore e to the power this del E by kBT will also increase. This will also increase, and therefore 1 upon 1 plus e to the power this del E by kBT, this will decrease. Alright, so we can see for energy, so this is the range E less than EF, and this is for E greater than EF, this is the range for E greater than EF. So having this relation, so basically we can see that as temperature is increasing, basically this Fermi-Dirac distribution, so what we have arrived is that as T increases, this F of E decreases. Okay, so this is what we have arrived for del of E greater than 0. Okay, for del of E less than 0. Just a minute. Okay, so for del of E less than 0, as temperature increases, the Fermi-Dirac distribution should decrease. So if you see this diagram, we can see that yes, for non-zero temperature the Fermi-Dirac distribution is decreasing. So it is decreasing in this. Let me just. Alright. So here we can see that here in this direction, this Fermi distribution is decreasing. So we know that this temperature is increasing. Alright, because we have found this relation that for del E less than 0, so this is the region. Del E less than 0 is this region. Hello. Are there any doubt? Hello. Yeah. Do you have any doubt here, or do you have any doubt, or can we continue? Hello, Shivani. Okay. Can you please switch off your mic? Oh, yeah. Thanks. In case you guys have any doubt, then you can switch on your microphone and ask the doubt between the session. But otherwise, please keep your microphones off. Alright. So okay. So basically, we can see. Sorry. Yeah. So here we can see that basically this in this direction, since the Fermi-Dirac distribution is decreasing, it means our temperature is increasing. Okay, so basically our temperature is increasing in this direction. So temperature is increasing. Alright, so that's why we can say that from here T3 is greater than T2 is greater than T1. This will be our final answer. Alright, now we could have reached this answer from the other direction as well. So here what we have seen is the range for energy less than EF, and we found that basically where del of E, here basically I let me write del of E is less than 0, and there del of E is greater than 0, where del of E is equals to E minus EF. Alright, so from here we can see that the temperature is increasing in this sense because the Fermi-Dirac distribution should decrease. Alright, but if we have used something else, so say if we have used that, if we see the range, like in the problem, if only this range is given to you, energy greater than EF is given to you, then in this case we have del of E is greater than 0. So as T increases, this del E by kBT, now this will decrease. Alright, the magnitude was decreasing and it is positive now, so this value will decrease. Therefore e to the power del E by kBT, that will also decrease, and therefore 1 upon 1 plus e to the power del E upon kBT, that will increase. Alright, so what we have seen that here, so what we have derived here is that as T increases, f of E also increases if del of E is greater than 0. Okay, so for the range where energy E is greater than EF, okay, del of E is greater than 0, it means E is greater than EF. In that range, as temperature increases, your Fermi-Dirac distribution increases, while for the range where E is less than EF, then in that case, as temperature increases, Fermi-Dirac distribution value will decrease. So here in this range, we can see that the Fermi-Dirac distribution should increase as temperature increases. So here we can see that, you can see that here the curve, here for T equals to 0 Kelvin, for E greater than EF, Fermi-Dirac distribution was 0, but now it is increasing. So this is the direction of increasing temperature. Alright, so here this is the direction of increasing temperature, and beyond EF, this is the direction of increasing temperature. So from here also we will get the same answer, that T3 is greater than T2 greater than T1. So from here also we will get the same answer, T3 is greater than T2 greater than T1. Right? Okay. Any doubt in this one? Okay. Alright, so this was our problem number 3. So let's go to problem number 4. So in problem number 4, what we have to do, we have to determine the energy dispersion relation for a square lattice using nearest neighbor tight binding approximation. So you have so I get in the lecture the tight binding approximation was done for the 1D case. So in today's session we will actually see a lot of tight binding examples. We will try to cover all of them. We will see the 2D and the 3D cases basically. So let's start with this first 2D case, which is a simple square lattice. So so this will be our square lattice. Alright. So this will be our square lattice. Yes. Alright, so this is our square lattice, this is our lattice parameter A. Alright, so to solve this problem, okay, and also let me just use this is my X and this is my Y. Okay, and let's say our the square lattice, it has this distance between each of the nearest neighbor, that is A. Alright, so if you take for a square, if you take, let's say this is our so I am going to denote this one of my this lattice point as m comma n. So here we can see that basically in a square lattice we are going to have four nearest neighbors. So I will define them as m plus 1 comma n. So why I'm defining is because basically we will solve these problems in terms of the lattice parameter basically. So here we have you can see that there are going to be two lattice parameter. We have an a1 vector along the x-axis and a2 vector along the y-axis, and the position of each of the lattice point, as you might know, the r vector will be the position of any of the lattice point that could be given by some integer a1 vectors plus times some integer times a2 vector. So basically today so all the problem that we are going to solve in this session, we are going to solve in this sense basically, that we will start with some particular lattice point, and then we will define other lattice point as some integer multiple of that lattice parameter. Alright, so if I define my this lattice point as m comma n, then I will try to find the so there are going to be four nearest neighbors. One will be will be at m plus 1 comma n, another one will be at m minus 1 comma n. Now this nearest neighbor I can label it as m comma n plus 1, and this nearest neighbor I can label as m comma n minus 1. Alright, so okay, now let the hopping integral is minus t. Okay, so let the hopping integral is minus t. Now using linear combination of atomic orbitals, it is LCAO. Alright, so using this linear combination of atomic orbitals, what we have psi of k vector r vector. So my wave function, I can write it as a linear combination of that has been done in the lectures as well. I can write it as e to the power iota k vector dot r vector psi of r vector small r vector. Okay, where this is going to be my LCAO, and this is going to be my atomic orbitals. Alright, so now I will take k vector as kx times x cap plus ky times y cap. Alright, and my r vector here, which is my real lattice parameter. Alright, so that will be ma times x cap plus na times y cap. Alright, so basically with r vector I can go to any of the lattice point. Okay, so it will be some integer times of the this a1 vector, which is ax cap, and n times of the a2 vector, which is ay cap. So I can write this psi k vector r vector as 1 by under root of n summation over m comma n. Okay, so summation is for m equals to 1 to n and n equals to 1 to n, considering we have n of these lattice points, e to the power iota kx ma e to the power kx ma e to the power iota ky na times psi of m n r vector. Alright, because it was psi of r vector, so I can write it as some psi m n r vector e to the power iota k vector dot r vector. If I do, then that will come e to the power iota kx ma e to the power iota ky na here. Alright, as we have a square lattice. Now, so basically from this, if you remember that like similar to your 1D case, basically in this case also we have like mn parameter, and basically they are going to be for each of these n terms. So if you have like this, if we have this square lattice 2D case as well, we will basically form a matrix where we will have the diagonal terms. Okay, diagonal terms will be equals to when m is equals to n. When we are talking about both the electrons, they are at the same lattice point. Okay, so we will have some diagonal terms, and then we will have the off diagonal terms. Okay, which will be the hopping terms. All right. So if you remember the your matrix formalism that you have seen in the class, so basically I can write the diagonal terms as so I will call them diagonal terms where m prime and n prime is equals to mn. So these kind of terms will be given by psi mn star h cap psi mn, that I will call as dx dy. Integration will be over dx dy. So that I will call as epsilon naught, which is just a constant, as we have as you might have seen in the lecture as well. And then I will create the off diagonal terms, which will be our non-zero off diagonal terms for this matrix. Okay, so basically I am writing terms for the HMN matrix. All right. So there will be an HMN matrix where we will have Mn and H cap Mn, you will have M prime N prime. So basically the matrix elements that we are going to have. So let me just can I this. So basically we will have this kind of terms. We are going to from when we will do the you will see that we are going to have this kind of terms. I guess okay. So this kind of terms we are going to have. So correspondingly we will do the diagonal terms. Diagonal terms will be basically where m prime and n prime equals to mn. But I guess let me just not write it in this form. I guess that will be just will get confusing. Sorry about that, because if we go into 3D, then it will be like higher dimensional matrices. So okay, let us skip to actually this term. Okay, so basically let him not write it like this. So first let me show you. Okay, so now basically we have our wave function like this. Alright, we can form our wave function now. So now if we have to find our this energy dispersion relation, so that will be equals to integration over psi k vector. Okay, so that is given by psi of k vector r vector in this bracket notation, Dirac notation. It is written like this, which is basically dx dy, integration over dx dy, psi of k vector r vector complex conjugate h cap psi of k vector r vector. Alright, now this we can write as we have seen here. So I will replace this with 1 by under root of s summation over some m prime n prime e to the power minus iota kx m prime e to the power minus iota kx m prime a e to the power minus iota ky n prime a times psi of m prime n prime r vector. Okay, so basically what I have not done anything. I have just written like, okay, this was our psi of k vector r vector, right? This is our psi of k vector r vector. I have just taken the complex conjugate of it. Complex conjugate will be e to the power iota, so will become e to the power minus iota kx ma, and I am taking summation m prime n prime instead of mn here now. Alright, and I have psi m prime n prime this complex conjugate star. Okay, then in this we will have an h cap. So let me just write it here. So okay, then I will have my operator, Hamiltonian operator h cap, and then I will write the this psi k of r vector. I will write this psi k of r vector as summation over mn e to the power iota kx ma e to the power iota ky na psi of mn r vector. Okay, any doubt up to this point? Okay, so this is a, yeah, I've just written psi k vector r vector as we have defined, as we have found here. So I've just written them. One is the complex conjugate and one is the this, and one is whatever the wave function is, and then in between we have the our Hamiltonian operator. Now this I can write it as okay, so 1 by root n, 1 by root n I will take out, it will be 1 by n. Now I will have summation over mn and summation over m prime n prime. Okay, and then I will take e to the power itas together, so it will be e to the power iota kx times a m minus m prime, e to the power iota ky a n minus n prime, and then we will have this integral dx dy psi m prime n prime star r vector h cap psi m n of r vector. Alright, and this integral I will denote it in this Dirac notation m prime n prime h cap mn. Okay, in this bracket notation I will denote it like this. So basically from here our energy dispersion now kx comma ky will be is equals to 1 by n. So let me just write it a little below. Energy dispersion kx comma ky will be equals to 1 by n summation over mn summation over m prime n prime e to the power iota kx a m minus n prime e to the power iota ky a n minus n prime times this m prime n prime, this matrix element m prime and h cap mn. Alright, so this will be our energy relation. Now we have to since we have to correct all the non-zero. So we know that we are not going to have all the terms are not going to be non-zero. Okay, most of the terms are going to be zero because we are just considering the nearest neighbor interactions only. So then we have to correct the non-zero terms. Okay, so from here we have to, from this summation we have to correct the non-zero terms. So since there are 4 nearest neighbors, okay, and we are just in this one we are just considering nearest neighbors only in this time continuum approximation. So we will have 5 non-zero terms. So there are going to be 5 non-zero terms. Alright, okay, so basically if you have n number of nearest neighbors, then from this summation you are going to have n plus 1 non-zero terms. Alright, so what are those terms are going to be? So the first case for m prime n prime is equals to mn. Okay, so when our m prime n prime, so we have basically summation of m prime n prime and mn. So first case will be when we have m prime n prime equals to mn. Or okay, let me just not write for because that will be just too much time consuming. So when your m prime n prime is equals to mn, then what will happen in this summation? So in this summation all these e to the power iota terms, they will be 1. So our term will remain m prime n prime will be mn, sorry, alright, yeah, so we will have mn h cap mn. Okay, so whatever, so just focus on this area basically. Basically what we are seeing, we are trying to see what will happen to these terms. Okay, what will happen when we change this m and m prime, and basically we know that the summations are going from 1 to n. So whatever the non-zero terms are going to be, so basically we are going to, since we have 4 nearest neighbor, we are going to have 5 non-zero terms, and we are going to get n times of this because the summation for each of these lattice point, we are doing the summation for each of the lattice point in this one, and n is going from 1 to n. So we will get n times of these 5 terms. So n and n will just cancel out. So at the end we will just get this 5 non-zero terms. Okay, I hope this is clear. Okay, so we are just trying to find out when this thing, this term which is within the summation, that is going to be 0. And this thing we are writing those 5 terms. We know that there are 4 nearest neighbor, so there are going to be 5 such terms. So first term will be when n prime is just mn. Okay, so we are just talking about so basically I have plotted this 5 purple points. So if I take, so we are basically going to have each of the term from this 5 purple points. Alright, so first term will be when n prime is just mn. So we are just talking, we are just at the that point. Then this e to the power iota, this will be e to the power 0, e to the power 0, so there will be 1 1, or we are left with mn h cap mn, which we will call our which we will call some epsilon naught. Okay, which is called the self energy, okay, or site energy, whatever you want to call it. Okay, it's just a constant. Okay, and most of the time we even take it 0. That's your choice. Okay, now next will be our so basically if we have like 4 nearest neighbors, so one term will be for the site energy. Okay, from this summation one term will be the site energy when n prime will be equals to mn, and the second term and the next 4 terms will be from the nearest neighbors. So for the nearest neighbor, we have seen that one case will be when n prime is m plus 1 comma n. Alright, so in that case what we will get, this e to the power iota, this n minus n prime, n is equals to n prime, so that will give me 1. From here I will get e to the power iota minus iota kx of a, because we have m plus 1, m prime, you put m plus 1, so this term will become e to the power minus iota kx of a. Alright, e to the power minus iota kx of a times we will have m plus 1 comma n h cap m comma n. So and this will be our hopping term, and the hopping integral we have considered it to be minus t, so it will be just equals to minus t e to the power minus iota kx of a. Okay, since this is square, we are just considering all the hopping terms to be same. Okay, then similarly we will have m prime comma n prime, next will be equals to m minus 1 comma n, so you will get e to the power iota kx of a. If you just put this m prime equals to m minus 1, and then we will have m minus 1 comma n h cap m comma n, which is again a hopping integral, which is we have considered minus t e to the power iota kx of a. Next term that we are going to have when m prime n prime equals to m comma n plus 1, we get e to the power minus iota ky of a. E to the power minus iota ky of a, m comma n plus 1 h cap m comma n. So this will give us minus t times e to the power minus iota ky of a, and then we will have m prime n prime equals to m comma n minus 1. We have e to the power iota ky of a, m comma n minus 1 h cap m comma n. So that will be equals to minus t times e to the power iota ky of a. Alright, so this will be our 5 non-zero terms. And then as I said earlier, basically this 5 terms, since summation is from 1 to n, this 5 terms will be repeated n times, so we will just get n times and we just cancel out, and we will be left with just with this 5 terms only. So our energy dispersion now, E kx comma ky, will be given by E naught minus t times e to the power iota kx of a plus e to the power minus iota kx of a plus e to the power iota ky of a plus e to the power minus iota ky of a. Right, and let me just put these things in brackets. Okay, so these 2 terms in brackets, and then we will have the same similar pair for ky, e to the power iota ky of a plus e to the power minus iota ky of a. Alright, and then you just have to use a simple relation. If you remember, use e to the power iota theta is equals to cos theta plus iota sin theta. Alright, just put it there. So what you will get is kx comma ky that will be equals to epsilon naught minus, so this term will give me 2 cosine of kx of a, and this term will give me 2 times cosine of ky of a. So I can take 2 common out. It will be epsilon naught minus 2 cosine of kx of a plus cosine of ky of a. Right. So this will be our answer for the square lattice. So this will be energy dispersion for the square lattice. E kxy is equals to epsilon naught minus 2t cos kx of a plus cos ky of a. Right. And here you can also see the bandwidth. So bandwidth is not asked, but if it is asked like what is the bandwidth for this energy dispersion, so you can see that the maximum value for this will be epsilon naught plus 4t, because the minimum value for cosine of will be minus 1 minus 1, so it will be minus 2 times minus 2 plus 4 minus epsilon, the lowest value, which is epsilon naught minus 4t, so it will be 8 times of t. Alright, so this will be the bandwidth for a square lattice energy dispersion. So why I am doing this, so I guess if you see Charles Kittel book Introduction to Solid State Physics, they have the formalism is a little different how to write. I am using this method, like defining it in terms of m comma n and then finding this thing. So because this kind of method is useful if you want to write a code for this. So if you want to write a code for this square lattice, then you will find that writing this thing in this way, like taking an this lattice parameter and taking this nearest neighbor as the integer multiples of this lattice parameter, like m plus 1 or n plus 1. So this you can I can see that that will be helpful if you have to write a code to do this to get the energy dispersion. Alright, so we are going to see a lot of problem using the similar method today. So and in the last problem on the 3-dimensional case, I guess you will get the picture very clear, like how it will be helpful if you want to code this stuff. Alright, any doubt in this problem? Alright, so let's go to our next problem. So okay, so the problem number 5. So here we have to again consider the tight binding model now for a rectangular lattice with lattice spacing a and b, and a is greater than b. Then it is asked that what is the energy dispersion. We just again have to find the energy dispersion, and if the two hopping integrals are w and v, so w is corresponding to hopping integral about along the lattice parameter a, and v is along the lattice parameter b, then which one would be larger one? Alright, so let us start with the energy dispersion. So for the rectangular lattice, let me make the rectangular lattice. And this, I guess in this this m comma n, this kind of method I believe is more intuitive as well to see like how each of the contribution is coming in the tight binding as well. So I prefer to do it like this. In Kittel, I guess Kittel is also, it is similar, but they have just written it in a little different way. So let's say, okay, so let's say this is our rectangular lattice, and these are our lattice parameter a and b. Okay, let this be my axis x and y. All right, and okay, and here it is given that okay, it is given that a is greater than b. All right. So again, similar to the square lattice, again, like if you take this one as your m comma n, then again we are going to have for rectangular lattice as well. We will have like 4 nearest neighbors, because we have to take the nearest neighbor in a 2-dimensional space. Okay, so although like you can say like these two are the nearest, and while these two along the a, they are not nearest, like they are farther away, but basically we are talking about a 2D tight binding model. So we want 2-dimensionally which are the nearest one. So within the 2 dimension, which are the nearest ones. So in the 2-dimensional space, these 4 points are going to be the nearest ones. Alright, and then again these will also be given by m plus 1 comma n. This point will be given by m minus 1 comma n. This is given by m comma n plus 1, and this will be given by m comma n minus 1. Alright, and here what are this w and v? So w is the open integral along the A lattice spacing, and V is the same hopping integral along the B lattice spacing. Alright, and remember that here, so here this W is less than 0 and V is less. Okay, so we know that this hopping integral we were using minus t, but here the hopping integral in the problem it is written that they are W and V. So, and we know that this hopping integral are going to be negative. Okay, we consider them to be negative. So remember that W and V are less than 0 here. Alright, now from LCAO we can see that psi of k vector r vector I can again write as 1 by under root of n same summation over r vector e to the power iota k vector dot r vector psi of r vector comma small r vector. Alright, then let's write our k vector. So k vector will be kx x cap plus ky y cap. Alright, and r vector will be here written by m a times x cap plus n b times y cap. Okay, because we have now different direction a and b, that is the spacing between the lattice point, it is different. So now our psi of k vector r vector, it will be given by 1 by under root of n summation over m comma n e to the power iota kx ma e to the power iota ky and b psi of m comma n of r vector. Alright, then similarly again what we have to do, again we will have these E of k vector energy dispersion. This will be again given by psi of k vector star r vector h cap psi of k vector r vector, and then we just have to open it up again. This time will be 1 by under root of n summation over m prime n prime e to the power minus iota kx n prime a prime m prime a e to the power minus iota ky n prime b psi of m prime n prime star r vector h cap 1 by under root of n summation over mn e to the power iota kx ma e to the power iota ky and b psi of mn r vector. Okay, and there will be dx dy, integration over dx dy. So from here again I will just take 1 by n out. The summation we will have mn summation over mn summation of m prime n prime. We will have e to the power iota kx a m minus m prime e to the power iota ky a ky b n minus m prime integration over psi of mn star r vector h cap, or let me just write it on this side only, integration over psi of dx dy psi of mn m prime n prime star of r vector h cap psi of mn r vector. Alright, and again basically this I will denote as m prime n prime h cap mn. So again we will get the similar kx ky, my energy dispersion will be a function of kx ky now. Alright, so energy dispersion we will have kx ky is equals to summation 1 by n summation over mn summation over m prime e to the power iota kx times a m minus m prime e to the power iota ky b n minus n prime times this n prime h cap mn. Alright, so here you can see that this rectangular case, as we expect, it is going to be, or it is similar to the square lattice case, only that there is difference of this a and b. Now we have to correct the non-zero terms from here. Okay, again the same thing, only the, since there are 4 nearest neighbors, we will have 5 non-zero terms. Alright, so first will be for m prime n prime equals to mn, we will get mn h cap mn. Alright, similarly, okay, e to the power, there will be e to the power 0, so there will be 1 1, which will be equals to epsilon naught. Second will be m prime n prime equals to m plus 1 comma n, so that will give me e to the power minus iota kxa. Right, we will have m plus 1 comma m plus 1 h cap. This will be m plus 1 comma n h cap mn, and here it is given that, so this m comma n, so we have seen that this m to m plus 1, the hopping integral is w, so basically this integral, that is going to be w, so we will have w times e to the power minus iota kx of a. Similarly, I have m prime comma n prime equals to m minus 1 comma n, this will be give me e to the power iota kx of a. Okay, m minus 1 comma n h cap m comma n, and then again this integral also, this is about the a axis, so this is also going to be w e to the power iota kx of a. Okay, similarly we will have m prime comma n prime equals to m comma n plus 1, here e to the power minus iota ky of a, m comma n plus 1 h cap m comma n, so this will be equals to and now this is the hopping in the b direction, for which integral is v, so it will be v times e to the power minus iota ky of a. Alright, similarly we have m prime comma n prime equals to m comma n minus 1, fourth nearest neighbor, so this will be equal to e to the power iota, sorry about that, it is b, along the y-axis it is b, m comma n minus 1 h cap m comma n equals to v times e to the power iota ky, okay, this will be b and this will be b. Alright, so this will be terms. So now again, so from here our this energy dispersion kx ky now, so that will be equals to, all these 5 terms will be repeated n times, so n will just again cancel out, but we will be left with epsilon naught minus epsilon naught plus w times e to the power minus iota kx of a plus e to the power iota kx of a. Okay, you just have to sum up all these 5 terms. Okay, plus b times e to the power minus iota ky b plus e to the power iota ky of b. Alright, so from here we get epsilon kx comma ky will be equals to epsilon naught plus the it will be 2w times cos of kx of a plus 2v times cos of ky times p, right? So this is going to be our answer. Oh, so we want 1 minute. Alright, so okay, so this is going to be our answer for the energy dispersion. Alright, then the other thing is asked us like what is the relation between W and V. So for this, remember that note that the magnitude of the overlap integral overlap energy, so let's say overlap energy decreases exponentially with the separation. Alright, so this thing you can check from Kitter as well. Actually, this exact line that is written in Kitter as well. So I've just taken it from there. So basically, you understand that these kind of integrals, okay, this m plus 1, okay, so this hopping integrals which we call, so they depends on the overlap between these atomic orbitals. So as we increase this lattice spacing, as we increase the spacing between the lattices, this overlap will decrease. Alright, so this overlap between two lattices, you see, okay, so this will starts to decrease, okay, here, okay, so here is the overlap, alright, okay, so and if we increase the spacing, then this overlap they are going to decrease, alright. So because of this overlap decreases, the magnitude of this integral that is also going to decrease, alright. So magnitude wise this interactions they will also decrease, okay, and this is shown also in Kitter as well. Use the formula, so where they have used this integral as gamma, like we use minus t, they have used a minus gamma in the tight binding model, and they have shown that it exponentially decreases with the separation. So as we increase the separation, this overlap energy it will exponentially decrease. So that's why, since A is greater than B, the separation along the lattice spacing A is larger. Okay, so the separation between the along the lattice spacing A is larger, so the overlap is weaker. Along the lattice parameter A, as compared to that along B. Now, therefore, W is going to be greater than V. Okay, and note that why I am saying it is note that W and V are negative. So basically, W is the hopping integral along the A axis, which is larger one. So the magnitude wise, W is going to be less than V. Alright, but remember that it is said in the question that it is the hopping integral is W, and we know that we are taking this hopping integrals are negative. So this hopping they give us the negative energy. So if its magnitude is less, but it is negative, so negative will just flip the sign. So W is going to be greater than V. Alright. Okay. Any doubt in this problem? Right. So this was our problem number 5. Okay, so let's go to problem number 6. So in problem number 6, what we have is we have to consider a triangular lattice with a lattice spacing A, and then we have to find what is the tidal bending energy dispersion relation is. Alright, so alright, so now we have a triangular lattice. So our triangular lattice looks like, so we have this is going to be our triangular lattice. Just draw the triangular lattice first. So you can see this is like triangular lattice, or you can also call it hexagonal lattice. Okay, so this is my triangular lattice, and let me just join these points, these lattice points. I'm just joining the nearest neighbors. Okay, so this you can see, this is a hexagon. Okay, and this is the A lattice. As I've been saying, the lattice spacing is A. So the distance between each of the lattice point, that is A. Now for this this one, now I will write A1 vector and E2 vector. So earlier, so now actually it will be actually more general way I will write. Earlier I didn't write it. So let's say E1 vector, E2 vector are our lattice parameters. So maybe just write it in blue. Okay, so let's say these are all going to be our lattice parameters. So for this lattice, our lattice parameter are going to be, okay, so earlier what we have in the square lattice, we have E1 vector was A times x cap and E2 vector was A times y cap. In the rectangular lattice, we have A1 vector is A times x cap and A2 vector was B times y cap. Okay, they were just along the x cap y cap. Now this lattice parameters, they are not along the this x cap y cap, but they are at some angle. So here A1, A2, these are our lattice parameters, lattice vectors. These are our lattice vectors. All right. So in the same way as we have done earlier. Now what we can take is again I will start with, let's say, this one, m comma n, and here we can see that in this case this is a triangular lattice or a hexagonal lattice, so we are going to have 6 nearest neighbors. So how I am going to define them? So let's say this neighbor, I can see that now this mn, they are basically, as there for square lattice it was A1 vector was just A times x cap, so that's why we have like m times, so basically this mn are basically integers multiplied to the lattice parameters. Alright, and earlier we have just x and y. So here this point, if this point is noted by mn, so each of the Rn vectors is given by m times of A1 vector plus n times of A2 vector. Okay, this is what we have been doing. So for any 2D lattice, we will define any of the lattice parameter as some integer times the lattice parameter A1 vector plus integer n times the A2 vector. Alright, so if I start with some lattice point which I am calling mn, then the next one will be written as this one, one neighbor, it could be m plus 1 comma n. This one will be m comma n plus 1, and this one could be, you can see if it is m plus 1 comma n, this one will be m minus 1 comma n. I'm just writing the coordinates in terms of the A1, A2 vectors. Then this will be m minus 1 comma n plus 1. This will be just n plus 1 comma n minus 1, just negative of that, you can see, kind of negative. And similarly, if it is m comma n plus 1, so this will be m comma n minus 1. Alright, so this will be our 6 nearest neighbor, and the coordinates I have given in terms of the lattice parameter A1 and A2. Okay, and let me just write this as, okay, let's say this is our x direction and this is our y axis, the Cartesian coordinates. Okay, now assume that the hopping integral between nearest neighbor sites is minus t. Okay, again we are just assuming this hopping integral to be minus t. Alright, so I will again start with this psi of k vector r vector is equals to 1 by under root of n summation over this r vector e to the power iota k vector dot r vector psi of r vector small r vector. Okay, where our k vector is basically equals to kx times x cap plus ky times y cap, and my r vector will be given by m times of a1 vector plus n times of a2 vector. Okay, otherwise I just write it at ax cap vector because a1 vector a2 vector like this, but this is how we define any lattice point. Alright, in terms we define them in terms of the lattice parameters, and here we have e1 vector is equals to a times of x cap and e2 vector will be equals to a by 2 of x cap plus root 3 a by 2 of y cap. So this I don't remember if we have done this problem. I guess we actually did it, like hexagon of the primitive lattice parameter, but I guess this is easy to find the these lattice vectors a1 and a2, and if you have any doubt then just try it on your own, and if you couldn't do it then I will try to show that in the next session. But I guess this is easy. So for hexagonal lattice, the lattice parameters are e times of x cap and e2 vector is a by 2 of x cap plus root 3 a by 2 of y cap. And I don't remember, maybe in one of these session I actually did it. I don't remember now. Just check it maybe. Okay, you can check it or you can check any solid state physics book. Okay, you can easily find this thing. Okay. So I hope this thing is easy. Okay, try to find out this a1 e2 vector, and I guess I had done it, but I don't remember now. So basically our r vector now will become ma plus na by 2 x cap plus root 3 a by 2 n times of y cap. Alright. So from here my psi k vector is my psi k vector of r vector. Now this would be written as 1 by under root of n, again I will have summation over mn. Now if you do a k vector, it is basically e to the power iota k vector dot r vector, and then if you do this, this is our k vector and this is our r vector. If you do the dot product, you will get e to the power iota kx or let me actually write it in another way. Okay, so basically it will be k vector dot, okay, so let me just write it in this form. So basically what we will have is, if I do this thing, so basically it will be, let me just write it in this form which will be more useful way. I can write it as e to the power iota k vector dot r vector could be written as m times of e1 vector. Okay, so basically what we will have is, since our r vector is basically m times of e1 vector, n times of e2 vector, e1 e2 vector are written like this. Alright, so you can write it like this, or basically I can also do it, we can also do it like this actually. So actually this will be more useful. K vector dot e1 vector, alright, e to the power iota n k vector dot e2 vector, and then I will have this psi of m comma n of r vector. Alright. I guess that will be, just let me check actually, should I display it? Okay, let's just do it in this way because that will be much more easier to do. Yeah, so this will be a better way actually. Okay, so I will write it like this. Okay, and what will be this will give me, you can just take the dot product from here, sorry, just use this one, a1 a2 vector. Alright, so okay, so from here I can write the summation of mn. So if you do k vector dot a1 vector, we just have an x cap. So you will get e to the power iota m times a, alright, a times kx, or I can write it as a kx times a. Alright, and if I do k vector dot e2 vector, which is this, I will get iota, and k vector dot e2 vector will give me a by 2 kx plus root 3 a by 2 ky times n, psi of m comma n of r vector. Any doubt at this point? Okay, this is clear, right? This is just I have written k vector dot a1 vector because m times k vector dot a, I have written this k vector dot r vector. R vector is m times a1 vector plus n times e2 vector, so this will become e to the power iota m k vector dot a1 vector plus e to the power iota n k vector dot e2 vector. Okay, so this will be like a general formula more. So this will be a more general formula. Okay, earlier we have a1 vector as ax cap, so we just have this, and e2 vector as a y cap for the square lattice. Now this is more general, and then I just put k vector dot a1 vector. K vector is this, a1 vector is this. Okay, k vector is this, a1 vector is this. Okay, so just do the dot product, you will get e to the power iota a kx times m, and then you can get k vector dot e2 vector will be just iota times a by 2 kx and root 3 a by 2 ky times n. Alright, so this will be our wave function now. So yes, okay, so now we will just do the same thing. Now we need to find the energy dispersion. So energy dispersion is k function of k vector, so that will be is equals to integration over again dx dy psi of k vector r vector star h cap psi of k vector r vector. Okay, again now just open it up. So okay, just 1 minute. Just 1 minute. Okay, sorry about that. Okay, let us come back to this. Okay, so basically we have like m prime n prime. I will just write e to the power iota, e to the power minus iota, I will have e to the power minus iota a kx times m prime, n to the power minus iota a by 2 kx plus root 3 a by 2 ky times n prime psi of m prime n prime of r vector complex conjugate. Right, then you will have a Hamiltonian operator h cap, then 1 by under root of n summation over mn e to the power iota a kx m e to the power iota a by 2 kx plus root 3 a by 2 ky times n psi of mn of r vector. Alright, So now, and this could be written as, again I will have summation of mn, summation of m prime n prime. It will be e to the power iota a kx m minus m prime, and e to the power iota a by 2 kx plus root 3 a by 2 ky n minus n prime. Alright, and then you will have your integration dx dy psi star m prime n prime h cap psi of mn. Okay, and again we know we are going about what we are going to do. So basically our e of now kx comma ky for this triangle lattice will be given by 1 by n summation over mn summation over m prime n prime e to the power iota a kx m minus n prime x b by 2 ky n minus n prime times we will have n prime h cap mn. Alright, so this is going to be our energy dispersion. Now again we have to again do the same thing. We have to correct the non-zero terms. Alright, and the non-zero terms will be n times repeated, so and then will cancel out. So correct the non-zero terms. Now again we have like 6 nearest neighbors. Okay, so we are going to have, so from in this diagram we have like 7 purple points. So we are going to have 7 terms because and we have like 6 neighbors. So there are 6 nearest neighbors. Six nearest neighbors. We will have 7 non-zero terms. Alright, so we will have 7 non-zero terms. So first will be for m prime n prime equals to mn. So that will be just here equals to this mn h cap mn, which will be equals to epsilon naught. Alright. Second will be m prime n prime is equals to m plus 1 comma n. So I will have from here I will have e to the power minus iota a kx m plus 1 comma n h cap m comma n, which will be this will be Hopper integral, so it will be minus t times e to the power minus iota a kx. Alright. Similarly, we will have m prime n prime equals to n minus 1 comma n. It will be e to the power iota a kx m minus 1 comma n h cap m comma n, that will be minus t times e to the power iota a kx. Alright, then next we will have m prime comma n prime. I can simply write m comma n plus 1. So it will be e to the power now if you have n plus 1, it will be e to the power minus iota a by 2 kx plus root 3a by 2 ky. So e to the power minus iota a by 2 kx plus root 3a by 2 ky times m comma n plus 1 h cap m comma n. So I can write it as minus t times e to the power minus iota. So I will just separate them. E to the power minus iota a by 2 kx, and it will be e to the power minus iota root 3 a by 2 ky. Alright. Then I have fifth term m prime comma n prime is equals to m comma n minus 1. So that will be equals to e to the power minus e to the power iota now, and we get a plus a by 2 a by 2 kx plus root 3 a by 2 ky, where m comma n minus 1 h cap m comma n. This will give us minus t e to the power iota a by 2 kx power iota root 3 a by 2 ky. Alright. Then next term will be for m prime comma n prime is equals to what we are left with. We have m plus 1. Okay, we have one m minus 1 and n plus 1. Okay, so we have m minus 1 m plus 1, so that will give us e to the power iota e kx. Alright, from this m minus 1, and for n plus 1 we will get e to the power minus iota times a by 2 kx plus root 3 a by 2 ky times we will have this m minus 1 n plus 1 h cap m comma n. Operating integrals are just minus t, and then this will become e to the power iota a kx by 2 and e to the power minus iota a root 3 ky times root 3 a by 2, or let me just write it as kx times a by 2 e to the power minus iota ky root 3 a by 2. Alright. Then we have the seventh term, which is m prime comma n prime is equals to m plus 1 comma n minus 1. Right. M plus 1 comma n minus 1. So that will give us e to the power minus iota a kx e to the power iota a by 2 kx plus root 3 a by 2 ky. And so this will be n plus 1 comma n minus 1 h cap m comma n will be minus t times e to the power now we get e to the power minus iota kx a by 2 and e to the power iota ky root 3 a by 2. Alright. E to the power minus iota kx a by 2 e to the power iota ky root 3 a by 2. So this will be our seventh term. So this will be our all the seven terms, and now we just have to add them. So our dispersion relation epsilon kx comma ky that will be given by epsilon naught minus t times. So if you sum them, I will take e to the power minus so we have e to the power minus iota ekx and plus iota ekx. Alright, so these two terms here, so I will just take this together, e to the power iota ekx. Okay, then so I will take these two terms together. Then what we can do is, so we have these four terms. So among these four terms, what I will do, I will take two combinations in the start. Okay, so just so here we can see that we can take these two combinations with this and this term, and I will take this and this term. Okay, so alright, so if I take these blue ones, the blue ones that I have taken, so I can take e to the power iota k minus t times e to the power minus t is taken common from all of them. I can take from the blue ones, I can take e to the power iota ky root 3 a by 2 as common, and just doing it to because this makes my calculation simpler. Alright, and I will have e to the power iota akx by 2 plus e to the power minus iota akx by 2. And similarly, if I from the green ones, I can take e to the power minus iota root 3a by 2 ky as common, root 3a by 2 ky as common, and the summation will be e to the power minus iota a by 2 kx plus e to the power iota kx a by 2. Alright, so this will be our energy dispersion. Then again we just have to it as we have done earlier. So this thing E of kx comma ky, it will be epsilon naught minus t times, this will give us 2 times of cosine of akx plus, from here I will get 2 times of cosine of akx by 2 times e to the power iota root 3a by 2 ky plus I will have 2 times cosine of again akx by 2 and e to the power minus iota root 3a by 2 ky. Right, and here you can see that from these two again we can take 2 times of cosine akx by 2 common. So what we will have epsilon naught minus t 2 cosine of akx plus 2 cosine of akx by 2, and I can take this e to the power iota root 3a by 2 ky plus e to the power minus iota root 3a by 2 ky. Alright, so from here we will finally reach our final answer. Energy distribution in form of kx comma ky, that will be equals to epsilon naught minus, I will take 2 common, e to the power minus 2t cos of akx plus 2 times, because this will give you 2 times cosine of root 3a by 2 ky, so there will be 1 2 here remaining, cosine of akx by 2 and cosine of root 3a by 2 ky. Right, so this is going to be our final answer. Alright, so this is our final answer. Okay, so this I have written as 2 times cosine of this thing. I have written as 2 times cosine of root 3a by 2 ky. So we have this 2 times this, and 2 I have taken common out, we can take common here. Alright, let me just check if my answer is correct or not. Okay, the final answer is minus 2t cosine of akx and 3 by 2 ky. Alright. Okay, so this is our energy dispersion for a hexagonal lattice or a triangular lattice. Any doubt in this problem? Till this point, any doubt? I know these are like very big calculation, but this will give you some idea. Okay, so this will be helpful. I hope like if you actually do some computational research or you want to, so this kind of, if you write the expression in this form, then that will be quite useful for you. Alright, so let's go to our next problem. This is problem number 7. So in problem number 7, so this is not a tight bending problem, just refresh us from like we have done a lot of like 3 tight bending problems, so let's just do something else. Okay, so you must be tired seeing the tight binding, so let's do some different problem, simple problem on Hall effect. So the problem is an electron beam enters a closed field velocity selector with a magnetic and electric fields of 2 millitesla, and the electric field is given, which is in this Newton per Coulomb. Alright, so respectively, so what is the velocity of the electron beam if it traverses the cross fields undifracted? Okay, so the velocity of the unperturbed beam of electrons with crossed fields is calculated by Vd equals to E upon D. Therefore, so basically this cross field will be given by E upon B. Yeah, we'll just show you in a second why it is E upon B. 6 into 10 to the power 3 Newton by Coulomb. So these are in SI unit only. So your answer is also going to be in SI unit. Minus 3. It was millitesla. 10 to the power minus 3 Tesla in SI unit. So it will be 3 into 10 to the power 6 meter per second. So this. So here you see that why I have written this as Vd. So Vd basically it is the drift velocity of the electron. So basically in the problem as I said it is a velocity selector, and you have some crossed field velocity selector. So basically what is happening, that thing happen in your Hall effect as well. So you have electrons moving in the x direction, you apply a magnetic field along the z direction, and then you create a Hall field in the y direction, Ey. Now the electrons will, so basically the electrons will be not deflected. Just 1 minute. So it is saying that the electrons, we have to find the velocity of the electrons which are not deflected. So basically in your Hall experiment, simple Hall experiment, these are the electrons which will move in the x direction. Okay, so the electrons which are moving in the x direction. So this is basically, it is asking the velocity, the drift velocity of your electrons moving in the x direction, which are not deflected by the magnetic field, magnetic, and which is creating this cross electric field. Alright, and how this formula comes in. So for this, just like a formula proof. So as you remember in Hall effect experiment, okay, so like let's say here our Vd is the drift velocity of electrons moving in x direction in the Hall effect experiment. In the Hall effect experiment. Okay, so the general, so we know that our this Hall coefficient RH is given by 1 upon minus 1 upon Ne. So this will be equals to Ey upon Jx upon Bz, where this is the Hall field. Okay, this is the field that is generated because of the deflected electrons, the electrons which get deflected, and the electrons which are not deflected, they will just move in the x direction. And we know that Jx we can write as minus Ne times Vd. Alright, so I can write minus 1 by Ne is equals to this Ey divided by minus Ne Vd times B. So your Vd, your drift speed of the electrons, drift velocity will be equals to Ey upon B, and B is in this is Bz. We have applied magnetic field in z direction. So this is how this formula comes in. This is the Hall electric field. And this is the applied magnetic field. Alright, field. So this is your right magnetic field, and that is your Hall electric field. So this type of problems could also come like someone instead of like asking like this, it is directly as like what is the drift velocity of the electrons in the Hall experiment, then you have to use this formula. Or maybe the velocity is given in the examiner could ask the Hall electric field. So you can find it like this. Alright, so this was a simple problem and Hall effect. Okay, so let's go to our last problem. This is also going to be a big one. So this last problem, this is also in the tight binding only. So let's just take a 2-3 minutes break. Just a minute. Not audible. Yes. Sorry, actually, yeah, just went there was something, so it was 2-3 minute break that I said. Okay. Not audible. Now you can hear me, right? Am I audible now? Can someone switch on their microphone, just tell me, or write in the chat? Okay, yeah, thanks. Okay, so sorry about it. Okay, so let's just start with our last problem of the session, problem number 8. So problem number 8 is, again we have to determine the energy dispersion relation for now it's for the 3D case. We have to find it energy dispersion relation for simple cubic structure, body centered cubic structure BCC structure, and the face centered cubic FCC structure using the nearest neighbor tight binding approximation. Alright, so before starting it, let me just write the general formula that we have been using till now. So basically what we are writing, so we use the linear combination of atomic orbitals. Okay, so this is basically the general way how tight binding model works. So basically we use the LCAO, linear combination of atomic orbitals, to write our wave function as this. Okay, 1 by under root and summation of r vector e to the power iota k vector dot r vector psi of r vector comma smaller vector. Like hopefully so in this 3D case I will write some general formula. So hopefully after that, if any kind of structure is given to you, like the mathematics could be complicated, but you will know how to proceed basically for that problem. Not most likely in this course, but maybe in future somewhere you might need it. So the k vector, I can write it as kx x cap plus ky y cap plus kz z cap. Alright, and now r vector, what we have been doing is and now we have the z cap, we have this in 3 dimension. So it is m times of e1 vector, n times of e2 vector, and m n l l. I will type l. So 8 l times of a3 vector. Alright. So from there I can write my psi k vector r vector, my wave function from the LCAO. I can write it as 1 by under root of n summation over m and l e to the power iota m times k vector dot e1 vector e to the power iota n k vector dot e2 vector and e to the power iota l k vector dot e3 vector. Alright, I have written e to the power iota k vector dot r vector. Just do the dot product of this k vector and this r vector, as we have done for the triangular lattice as well, and then for the 3-dimensional case we will get this times our whatever our atomic orbitals are, psi m and l of r vector at that lattice point. Alright, so our energy dispersion now. So if I have to write the energy dispersion, again the same thing. This time it will be just I will just write it as dr vector. So dr vector is just dx times dy times dz. So let me just write it here. So this dr vector you can write as dx dy dz, but I am just now writing it as dr vector because we know that we are just going to write it in some this bracket notation. So it doesn't matter to write it in dx dy dz. So I'm just going to write it as dr vector times psi k vector star r vector complex conjugate h cap psi k vector r vector. Alright, so now I will just open my this wave functions. So I can write it as 1 by under root of n e to the power minus iota m k vector dot a1 vector e to the power minus iota n m plus my mistake, I have to do a summation. We have summation over m prime n prime e to the power minus iota k vector minus iota m prime k vector dot a1 vector e to the power minus iota n prime k vector dot e2 vector e to the power minus iota l prime k vector dot a3 vector. Alright, times psi of m prime n prime l prime times r vector complex conjugate. So this will be our psi k star of r vector. Then we will have our Hamiltonian h cap, and then we have 1 by under root of our summation over mn e to the power iota m k vector dot a1 vector e to the power iota n. Just 1 minute. Alright. So this will be e to the power minus iota n k vector dot a2 vector e to the power iota l k vector dot a3 vector times psi m and l of r vector. Alright. Then again we can take out this 1 by n here, so I can write this ek vector now. Again in the similar manner, we can write this ek vector as 1 by n summation over m prime n prime l prime. Okay, so sorry, it is m n l prime and m n l. We are in 3D now, and it will be m and l. Right, I will have e to the power iota k vector dot a1 vector times m minus m prime e to the power iota k vector dot a2 vector times n minus n prime e to the power iota k vector dot a3 vector times l minus l prime times we will have so I'm just writing, okay, we will have this integral. I'm just writing that integral as this, which will be m prime n prime l prime, because I have already done it quite several times. So I hope you understand that how we go from how we get from here to here. I'm just now directly writing this integral in this bracket notation. Alright, so this will be our in general if any for any three-dimensional lattice, and in case you have to 2D, just remove your one of the indices. Okay, if you have to go, so this is actually the more general tight binding formula. This is the general tight binding formula that we have. And okay, so I have written it for 3D, and then you can just go from 3D to 2D. Okay, right, so let me just zoom on. Okay, so this is our more general formula. For going from 2D, we just remove one of the indices, we will go to 2D, and if you remove two of the indices, then you will go to 1D. Alright, and okay, so you just have to use this formula. Right, now let's just go to our present problem. So what we have here, so first let me just start writing in this color. Okay, so our part A is we are asked for a simple cubic. Okay, simple cubic lattice. We have a simple cubic lattice. Now for a simple cubic lattice, what are the stuff that we have? So there are 6 nearest neighbors. Okay, for a simple cubic we have 6 nearest neighbors, and we have lattice parameter. So basically in this formula that we have derived, now to find the energy dispersion, what we need to know is we just need to know what are the lattice parameters. Okay, what are the lattice parameter for this lattice, and what are the how many nearest neighbors are there. Okay, and what are the coordinates of those of these nearest neighbors in terms of these lattice parameter, which are given by integers which are given by these integers m primes. Alright, so those are the things that we need to find. So we need to know this m prime, n prime, and l prime. Okay, what are the nearest neighbor terms, nearest neighbor coordinates are, and also we need to know find this find this lattice parameters. What are the lattice parameters? So for the simple cubic, we have a1 vector is a times x cap, a2 vector is a times y cap, and E3 vector is A times Z cap. Alright, so basically if you code this thing, then you know that your program will just need to know, okay, if you code this thing, your program will just need to know what are the primitive lattice parameters. You just need to provide those lattice parameter A1, A2, A3, and the integer values for this m prime, n prime, and l prime, like which are the nearest neighbors. Alright, so then you can do this using this method. You can just find the type binding method for any of the lattice. Alright, so let's say for the simple cubic, okay, so for simple cubic, so let me just make a simple cube now. So let's say this is my simple cubic structure. Alright, so 3D. Okay, and then you can make similarly. I can just extend it here, and this will be like my cube, right? And then you can make, okay, you can extend it further, like something going outwards you will have one, and going inwards as well you will have one. Okay, let's make this cube. There will be one will be here as well. Let me just do it. Okay, so it might not look exactly like cube, but my drawing is not that good, sorry about that. But basically you will have some, I hope you can imagine. Okay, so this is like your simple cube. Okay, like this is one simple cube, and if you expand it in the infinite space, like this is your one cube. Okay, this is your one cube, and then you just repeat those cubes in the in your space to make a cubic lattice. Now here also we have, let's say this is our x direction, let's say this is my y direction, and let's say this is my z direction. Okay, now distance between each of these lattice points, that is A. Okay, that I am taking as A. Okay, so let me just write it here. Okay, then let's say I am taking this one as my m comma n comma l. Okay, these are the coordinates for my this lattice point, one of the lattice point. Now here my lattice parameters. So where are my lattice parameters? So first you need to find the lattice parameter. So lattice parameter will be A times x cap. It will be around this. A2 will be along this, and A3 will be along this. Alright, so if these are my lattice parameter, so then my nearest neighbors are, so one of my nearest neighbor will be this, and its coordinates are going to be m plus 1 comma n comma l. Alright, so similarly I will have another another neighbor here, whose coordinates are going to be m comma n comma n comma l. Then I will have one neighbor here. Its coordinates are going to be, I am going in the minus 5, so it will be m comma n minus 1 comma l, and this will be m comma n comma n plus 1. Sorry about to change that. Sorry about that. There's some battery issue or something with the laptop. Alright, so yeah, so where will be, okay, yeah, it will be n plus 1 comma l. Similarly I will have this one will be m comma n comma l plus 1. Okay, we have to go to along the A3 and then along the minus A3, so there will be m comma n comma l minus 1. So these are going to be our 6 nearest neighbors, and these are the coordinates of those 6 nearest neighbors in terms of the lattice parameters. If someone wants to join, okay, we are about to end the session. Alright, So our this dispersion relation now, so I can write it as 1 by n summation over m prime n prime l prime summation over m and l. Okay, it will be e to the power iota kx times a. So I am just doing we have this formula. I will just put the k vector will remain just kx times x cap plus ky times y cap plus k times z cap. All right, it will be just that, and e1 vector, e2 vector, e3 vector are this. So we will get e to the power iota kx times a m minus m prime e to the power iota ky times a n minus n prime, and we have e to the power iota kz times a l minus l prime times we will have our m prime n prime l prime h cap m and l. Okay, some form of metric segment. Now again we have to, what we have to do, we have to correct the non-zero terms from this expression. Okay, so correct the non-zero terms, and again even for the 3D case as well, again the summation is for the up to the n number of sides. So all these non-zero terms will be repeated in the summation n times, and then they just cancel out, and we will left with just this non-zero terms. Now since there are 6 nearest neighbors, okay, here again you can see that basically the number of terms will be equal to the number of purple points. So we have one is this MNL, and then we have 6 nearest neighbors, so we have 7 points here. So since there are 6 nearest neighbors, we will have 7 non-zero terms. Alright, so what are those terms are going to be? So first will be m prime, n prime and l prime equals to m and l, okay, which is our self energy. So in that case but we will have that m and l h cap m and l only. Alright, e to the power iotas they will have 1 values, e to the power 0. So that will be equals to self energy epsilon naught. Then next case will be m prime, n prime and l prime, that is equals to m plus 1 comma n comma l. So that will be e to the power, okay, so that will be e to the power minus iota k, okay, so that will be e to the power minus iota kx of a times m plus 1 comma n comma l h cap m comma n comma l. This will be minus t times e to the power minus iota kx of a. So third will be m prime, n prime and l prime is equals to m minus 1 comma n comma l. So it will be e to the power iota kx of a m minus 1 comma n comma l h cap m comma n comma l. We will get minus t times e to the power iota kx of a. Then next will be n plus 1 comma l will be e to the power minus iota ky of a times m comma n plus 1 comma l h cap m comma n comma l, which will give me as minus t e to the power minus iota ky of a m prime comma n prime comma l prime will be equals to m comma n minus 1 comma l e to the power iota ky of a m comma n minus 1 comma l h cap m comma n comma l, And again, so these are the hopping integrals. I didn't say it, but we are going to take them to be same, minus t for all the hopping nearest neighbor sites. We get e to the power iota ky of a. Then we will have our sixth term, which will be m prime comma n prime comma l prime equals to m comma n comma l plus 1. This is get e to the power minus iota kz of a times n comma l plus 1 h cap n comma l minus t times e to the power minus iota kz of a. And then seventh will be m prime n prime and l prime equals to m comma l minus 1 e to the power iota kz of a m comma l minus 1 h cap n comma l minus t times e to the power iota kz of a. Alright, so this will be your 7 terms. So these are similar to your square case, but now we are in 3D, so we have 6 nearest neighbor. So in 1D we have 2, and 2D we had 4 in the square lattice, and now for the cubic we have 6 nearest neighbors. Alright, so if you just sum up all these 7 terms, and these 7 terms will be repeated n times, so n will cancel out there. So we will get our energy dispersion will be a relation of kx, ky, kz, that will be equals to epsilon naught minus t times, we will get e to the power iota kx of a plus e to the power minus iota kx of a plus e to the power iota ky of a plus e to the power minus iota ky of a plus e to the power iota kz of a plus e to the power minus iota kz of a. Alright, and again this will, as we know, it will become 2 times cosine of kx of a and so on. So our final energy dispersion will be equals to kx comma ky comma kz epsilon naught minus 2t cos of kx of a plus cos of ky of a plus cosine of kz of a. Alright, and okay, so this is our final answer. This is our energy dispersion, and it is not asked, but if we have to find the bandwidth. So this was asked in your assignment problem, one of the assignment problem. So if we can see that in this case also it will be epsilon naught plus 1 plus 1 plus 1. Okay, so maximum value would be when each of them cosine will be minus 1. So that will give you minus 3 times minus 2 will be plus 6. So epsilon naught minus plus 60 minus, which is the maximum energy, minus the minimum energy will be epsilon naught minus 60. So the bandwidth will be equals to 12 t. So this was the question in one of the assignment as well. So the answer, I guess if it is given 12 in that one. So this is how it comes. Okay, so we are already out of time for this session. It's already 6 p.m. So yeah, so the remaining 2 parts, the for BCC and FCC, we will you can try on your own. So basically, as you know, this is the formula that you have to use. Okay, and just you just need to know the nearest neighbors, and you just need to know your lattice parameters. Okay, you need to know your lattice parameters, and then you need to know, okay, you need to know your lattice parameter, and then you need to know your nearest neighbors and their coordinates in terms of the lattice parameter, and then just put them in this formula, and then just correct the non-zero terms, and that will give you tight binding dispersion relation. Alright, so just try out for BCC and FCC on your own, and we will try to discuss them in the next session. In the start of the next session, I will do this thing, and then we will continue that week 6 problems. Alright, any doubts from the problems in this session? Okay, if there are no doubts, then we can okay, and so we can just end this session now. If there are no doubts, then we can end this session. Okay, so there are no doubts. Okay then, thank you. Bye. Request.